a laser aimed straight down at the North Sea. On New Year's Day 1995, it measured a wall of water 25.6 meters high, in a sea whose worst wave should have been half that. Sailors had reported walls like that for 2 centuries and been quietly filed as exaggerators. Veteran crews fear the Drake Passage, Cape Horn, the Agulhas, Hatteras, the Bering, Biscay, Bass Strait, the Columbia Bar. Storms, they say. That answer is incomplete. The worst of those stretches are the shallow ones. And the same trap has closed on square riggers, an oil rig, and a satellite-tracked cargo ship. The laser was not there to make history. It was there because the Draupner E platform sat in about 70 meters of water, roughly 160 kilometers southwest of the southern tip of Norway, holding up a gas pipeline junction. And the engineers who built it wanted to know how much the sea was actually doing to their steel. So they bolted a downward-looking rangefinder to the underside of the deck and let it stare at the water 20 times a second, day after day, for years. It was a maintenance instrument. It logged numbers nobody expected to read. At around 3 in the afternoon on 1st January 1995, in a storm that was serious but not exceptional, the laser recorded a single crest that rose roughly 18.5 meters above the still water level and dropped into a trough deep enough that the total height from bottom to top came to 25.6 meters. The waves on either side of it were ordinary. The significant wave height that afternoon, meaning the average height of the biggest third of the waves, was close to 12 meters. Rough, unpleasant, entirely normal for the North Sea in winter. And then one wave came through that was more than twice the size of its neighbors, arrived alone, and left. Understand what that number meant to the people who read it. Ship design, platform design, insurance, classification rules, the entire arithmetic of what a hull has to survive rested on a statistical model of the sea in which waves behave roughly like a random sum of gentle sine curves. In that model, a wave twice the significant height is not impossible, but it is so rare that you would expect to wait tens of thousands of years to see one at a given spot. Draupner's laser saw it inside a single afternoon, on a platform that had been instrumented for less than a decade, in a storm nobody would have written home about. That is the part that should bother you. The rules were not slightly wrong about how big waves get. They were wrong about what kind of thing the ocean is. Before Draupner, the reports existed. They had always existed. Masters wrote in their logs about a hole in the sea with a wall behind it. Officers described watching a bow drop into nothing, and the horizon replaced by a vertical face of green water. Insurance surveyors read those accounts, compared them to the mathematics, and concluded, reasonably given the mathematics, that frightened men in the dark overestimate. Whole ships went missing on routes where the weather reports afterward showed nothing worse than a strong gale, and the files were closed with words like structural failure or cause undetermined, because there was no accepted physical process that could take a large modern vessel apart in a moderate storm. The laser did not solve those cases. It did something narrower and more disturbing. It proved that the process existed. And once the process existed, a second question opened immediately. And it is the question this whole story runs on. If the ocean can build a wave like that anywhere, out of nothing but chance, then geography must be able to build them on purpose. Somewhere there must be places where the shape of the seafloor, the direction of a current, and the arrival of a particular kind of weather stack, the odds so hard that the freak event stops being freakish and becomes a feature of the route. There are. Sailors have known where they are for a very long time. They just could not explain them. And being unable to explain a thing is a poor defense against it. The clearest of them sits off the eastern shoulder of South Africa, on a stretch of coastline the locals call the Wild Coast, between roughly East London and Durban. On a chart, it looks generous. Deep water close in, no reef systems to speak of, a straight run that saves a ship serious time on the passage between the Indian Ocean and the Atlantic. It has been one of the busiest tanker roads on Earth since the Suez Canal closed in 1967 and the very large crude carriers started going the long way around. Every day, hulls 300 meters long and loaded to their marks pass within 20 or 30 kilometers of that beach. What the chart does not show is the current. The Agulhas runs southwest down that coast, hugging the edge of the continental shelf, and it is one of the fastest major currents in the ocean. In its core, it moves warm Indian Ocean water at speeds that regularly exceed 2 meters per second and in places more. Put that in terms a person can feel. A cargo ship steaming southwest picks up 4 or 5 knots for free. Captains have used it for a century and a half. It is money. Fuel saved, hours saved, schedule kept. On a route where the arrival window is contractual, the Agulhas is not a hazard on the chart. It is a competitive advantage. Now bring the weather in. South of Africa, there is nothing but the Southern Ocean, and cold fronts march east across it in an endless procession. Each front drags a southwesterly gale behind it, and each gale pushes swell northeast, up toward that same coast. So you have a fast current running southwest and a large swell running northeast, and they meet head-on along a narrow ribbon of water at the shelf edge. The physical part is worth slowing down for because everything that comes later is a variation on it. A wave in deep water is not a lump of moving water. It is a pulse of energy traveling through water that mostly stays put. That pulse has a length, crest to crest, and a speed, and the two are locked together. Now run that pulse into a current flowing the opposite way. The wave still has to carry its energy forward, but the water it is traveling through is sliding backward underneath it. Relative to the seabed, the wave slows down. Its energy has nowhere to go, so the wave shortens. The crests bunch up. And because the total energy is conserved while the length shrinks, the height goes up. Shorter and taller at the same time. That is the entire problem in 5 words. A wave 300 meters long and 8 meters high is a long, rolling hill. A ship rides over it. Compress that same wave to 150 meters long and 12 meters high, and it stops being a hill. The face steepens until the water at the crest can no longer stay attached to the wave and it breaks. Not the way surf breaks on a beach spilling, but plunging, throwing tons of water forward and down with real velocity. There is a second effect, and it is the one that turns a bad sea into a killer. The Agulhas is not a uniform river. It has a fast core and slower edges, and it meanders. A wave crossing from slow water into fast water bends, exactly the way light bends going into glass. Bend a wavefront and you can focus it. Different parts of a long swell train, arriving from slightly different angles, get steered by the current structure into the same small patch of ocean at the same moment, and they add. For a few seconds, in a patch a couple of 100 meters across, the sea builds something that the surrounding sea state cannot explain. Crews who have survived it describe the same sequence with unnerving consistency. An unusually deep trough first, so deep that the ship pitches bow down into it, and then the wall. The man who first assembled this into evidence rather than folklore was J.K. Mallory, a South African oceanographer, and his 1974 paper in the International Hydrographic Review is still the anchor for everything that followed. Mallory did not theorize first. He collected. He went after the masters and officers of ships that had been damaged on that coast and got their positions, their headings, their weather, their descriptions. Then he plotted them. The plot did the arguing for him. The incidents were not scattered across the whole coast. They clustered along the 100-fathom line, which is the outer edge of the continental shelf, right where the current core runs, near submarine canyons that cut into that shelf, and overwhelmingly in the hours around the passage of a cold front, when the southwesterly wind sea was piling on top of an existing swell and both were running into the current. 3 ingredients: the shelf edge, the canyon topography, and frontal weather. None of them is dangerous alone. A strong current is a gift. A long swell is a comfortable ride. A cold front is a weather event that happens hundreds of times a year in that part of the world without consequence. Put all 3 in the same place, and they build something that has broken ships in half. That is the first thing to take from this. And it undercuts the obvious answer to why these waters terrify professionals. It is not the strength of the storm. Some of the worst documented encounters on that coast happened in weather that a deck officer would describe as a fresh gale. The danger comes from a geometry, a current direction, a bottom contour, a swell angle. And geometry does not need a hurricane to be lethal. It just needs the pieces to line up. Which raises the obvious follow-up. If this coast has been doing this for as long as there have been ships on it, where is the evidence? Where are the wrecks? That is where it gets strange, because the most famous casualty of that coastline produced no wreck at all. On 26 July 1909, the steamer Waratah left Durban for Cape Town. She was a year old, 150 meters long, built on the Clyde for the Blue Anchor Line to carry emigrants out to Australia and cargo back, and she was carrying 201 people. She had a reputation among some of her passengers for rolling heavily and being slow to come back upright, and at least one man who had traveled on her earlier had complained about exactly that. She had also crossed the Indian Ocean repeatedly without incident, which is the sort of fact that reassures everyone until it doesn't. In the early hours of 27 July, she overhauled the Clan Line steamer Clan McIntyre off the coast of Natal. The 2 ships exchanged signals by lamp. Waratah, faster, drew ahead through the morning and was last seen from Clan McIntyre's bridge at around 9:30, pulling away to the southwest, down the current, in weather that was deteriorating but not yet severe. She was due in Cape Town on 29 July. She never arrived. What followed was one of the largest searches of its era. The Royal Navy sent ships. Chartered vessels quartered the coast for months. Insurance underwriters, the Blue Anchor Line, and eventually the families paid for expeditions that swept the wild coast and then the open ocean toward Australia on the theory that she had been disabled and drifted. Nothing came back. No lifeboat, no confirmed body, no deck chair, no oil, no wreckage that could be tied to her with any confidence at all. The Board of Trade Inquiry in 1910 recorded that the ship had been lost in a gale, that she had probably capsized, and that the exact cause could not be established. That verdict has stood for more than a century because nothing has come along to replace it. People have tried. In July 1999, the marine explorer Emlyn Brown announced he had located the wreck off the Eastern Cape after almost 2 decades of searching, and for a short while, the mystery looked closed. Divers reached the site in 2001 and found the Nailsea Meadow, a British cargo ship torpedoed in the Second World War. Brown eventually said publicly that he had run out of leads and stopped. As of now, no confirmed wreck of the Waratah has been found. So be honest about what this proves. It does not prove that a rogue wave killed her. Nobody can prove that. What it proves is that a large, modern, well-found steamship can vanish on a 2-day coastal passage in a region with heavy traffic, in weather that other ships in the same water survived without difficulty, and leave behind an absence so complete that a century of searching produces nothing. That absence is itself information. Ships that founder slowly leave a trail. Boats get launched, gear floats free, people get into the water, and some of them are found. An absence that total suggests a very fast event. A ship going over or going down, in a period measured in minutes, with hatches and doors closed against the weather, in water that carried the debris out and away. The current that made the passage fast is very good at removing evidence. For 60 years, that was all anybody had: a missing ship and an unfalsifiable theory. The proof arrived in 1968 in a form nobody wanted. On 13th of June 1968, the tanker World Glory was steaming down that same coast, loaded with 334,043 barrels of Kuwaiti crude, bound for Huelva in Spain. She was a large ship for her time, and she was doing the ordinary thing, using the Agulhas, running southwest along the shelf edge, making good time. The weather that day was a southwesterly gale with a heavy swell, overcast, poor visibility, uncomfortable, not survival conditions. A tanker of that size is built to work in far worse. About 65 nautical miles east-northeast of Durban, she broke in two, not flooded, not holed, broke across the middle as a structure. The stern section stayed afloat for roughly 2 hours and then sank. The bow section did not sink immediately. It drifted southwest, carried by the same current the ship had been using, and the entire cargo eventually went into the Indian Ocean. The first major documented oil spill in South African waters. Of the 34 crew aboard, 10 survived. Some accounts give the complement as 35, and casualty figures in the older sources vary by 1 or 2. The survivor count of 10 is consistent across the record. So what does that failure teach that the Waratah could not? A ship is a beam. It is supported along its whole length by water pressure, and the designers calculate the bending loads on the assumption that the support is more or less continuous. Now take a hull 300 meters long and put it into a sea where the waves are, say, 180 meters apart and steep. Two things can happen, and both are bad. The ship can be lifted amidships on a single crest, with bow and stern hanging over nothing, which tries to fold her downward at the ends. Or she can be supported at bow and stern by 2 crests with the middle over a trough, which tries to break her upward in the middle. Naval architects call these hogging and sagging, and every hull is built to take them within a range. The range assumes the waves are longer than the ship, or at least comparable. Current-shortened waves are not. That is precisely what the Agulhas does. It takes a long, safe swell and compresses it. And when a wave gets short, relative to the hull, and steep at the same time, the bending moments go outside the design envelope, and they do it in a sea state that the officer on watch would describe accurately as a gale. So be blunt about it. The World Glory was not overwhelmed by a storm. She was taken apart by geometry. The sea did not have to be big, it had to be the wrong shape, which leaves an ugly question hanging. If a South African oceanographer could work this out by 1974 from interviews and a chart, and if a tanker had already been broken in half in front of witnesses in 1968, why were ships still being designed as though it could not happen? The answer is not stupidity. It is that the rules were built on a mathematical description of the sea that had been enormously successful everywhere else. Wave statistics were treated as a random process, lots of small independent components adding up, and that model does a beautiful job of predicting how often you will see a wave of a given size in an ordinary seaway. Classification societies used it to define a design wave. Insurers used it to price risk. Regulators used it to certify hulls. Everyone was using the same tool. The tool worked, and the tool contained an assumption that waves do not gang up. Real water does gang up. In a steep sea, waves stop behaving independently. Energy can transfer between them and pile into a single crest, and a current gradient can steer separate wave trains into one point. Both effects are nonlinear. Both were understood in principle by physicists, and neither was in the design rules that ships were actually built to. So the industry had a mechanism nobody had confirmed, a set of casualties nobody could explain, and a design standard that quietly excluded the mechanism from consideration. That standoff held until an unmanned laser in the North Sea logged a wave. The standard said, should not exist for another 10,000 years. Dropner did not just measure a wave, it broke the tie. The tie having been broken, the obvious next question was how often. One measurement is an anecdote with a serial number on it. In August and September 2001, a European project called MaxWave pointed two radar satellites, ERS-1 and ERS-2, at the ocean and told them to look at the surface rather than the weather. Radar of that kind can image a patch of sea and extract the wave field from it. Over 3 weeks, the satellites returned about 30,000 small images, each covering a few kilometers of ocean, scattered across every ocean on the planet. In those 3 weeks, in that tiny sample of the world's water, they found 10 individual waves higher than 25 meters. 10 in 21 days. In a sample that covered a vanishingly small fraction of the sea surface at a vanishingly small fraction of the time. The statistical models in use at the time predicted something on the order of one such wave somewhere on Earth, in a period measured in decades. The satellites found 10 in 3 weeks and were not even looking hard. The implication was not that the models needed adjusting. It was that giant waves are a normal, continuous feature of the ocean, occurring somewhere at almost all times, and that the reason nobody had proved it was that ships are small, and the ocean is enormous, and the encounters are rare from the point of view of any one vessel. That changed what could be said about the unexplained losses. Not solved? Said. There is a difference, and it matters. Consider the München. She was a German ship, a lash carrier, a design that carries loaded barges rather than containers, so she was large, modern for 1978, and built to a high standard. On 7 December 1978, she left Bremerhaven for Savannah, Georgia, with 83 loaded barges of steel products and 28 crew, into a North Atlantic winter. Just after midnight on 12th of December, her radio officer spoke to a colleague aboard a German cruise ship 2,400 nautical miles away, reporting heavy weather and some damage. That was the last coherent communication. Fragmentary distress signals followed. Then nothing. The search that followed was one of the largest ever mounted in the Atlantic. Over 100 ships and dozens of aircraft. They found very little. And one of the things they found is the single most quoted piece of physical evidence in the entire history of this subject. They recovered one of the München's lifeboats. It had been stowed on davits about 20 meters above the waterline. The pins that held it should have been hanging vertically. They had been bent backward, from forward to aft. Think about what that requires. Something struck that lifeboat hard enough to tear it from its fittings and bend the metal in the direction of travel, 20 meters above the sea. Not spray, not green water sloshing along the deck. A mass of water arriving above the level of the bridge deck with enough momentum to reshape steel. The investigation of the time could not name the cause because in 1979 the mechanism was not officially acknowledged to exist. The finding was, in effect, that severe weather had produced an unusual event. 28 men were gone, and the file said that. Now go back to the Agulhas with that in mind, because the most useful evidence there does not come from the ships that sank. It comes from the ones that made it home broken, because a survivor brings the damage back with her and lets a naval architect measure it. On the 2nd of May 1973, the cargo liner Ben Cruachan was about 74 miles southeast of Durban, steaming into a head sea while working down the current. She was struck by a very large wave. It fractured her hull. She did not sink. She was got into Durban for temporary repair and then made Rotterdam at reduced speed for permanent work. And every plate and frame she came in with was available for inspection. The same year, on her maiden voyage in the same waters, the tanker Neptune Sapphire met the classic sequence. She went into a hole, and the wave behind it hit her forward. The ring of the hull fractured around the bulkhead between her first and second holds, and the bow, some 60 meters of ship, broke away and sank. The rest of her was towed into East London. Read that again slowly. A brand new tanker lost the front 60 meters of herself and stayed afloat, in weather that did not sink any of the other ships on that coast that day. 3 ships in 5 years on the same stretch of water, none of them sunk by flooding. All 3 failing as structures. 1 across the middle, 2 in the forward body just aft of the bow, which is exactly where you would expect steel to go if a hull pitched down into a deep trough and had a steep face land on it from above. That is the pattern the missing ships were part of. The Waratah cannot be proved to belong to it. The World Glory can be argued about. Bencruachan and Neptune Sapphire cannot be argued about at all, because their damage was photographed, surveyed, and repaired. And the repair bills are in the record. That inverts what most people assume about maritime evidence. The wrecks tell you almost nothing. They are unreachable, scattered, and silent. The ships that come home with their bows missing are the primary source. Every serious step forward in understanding this mechanism. Mallory's survey, the design work that followed, the eventual acceptance by the classification societies that a design wave has to account for steep, breaking, focused seas rather than smooth statistical ones, came from damaged survivors and eventually from instruments that do not get frightened and do not exaggerate. And here's the part that stings. While engineers and underwriters spent 70 years waiting for instrumentation to settle an argument, there were people on those same coasts who had already solved the problem. Not by understanding it, but by refusing to be in the wrong place when it happened. Every one of these dangerous stretches had people living beside it long before anyone drew a chart of it, and those people crossed the water routinely. Torres Strait Islanders worked a maze of reefs, tidal races, and shifting channels between Australia and New Guinea in outrigger canoes. Maori crossed Raukawa Moana, the strait between the 2 main islands of New Zealand, where the tide runs hard enough to stop a modern ferry from making headway. Unangak's crews in skin-covered bidarkas hunted far offshore in the Bering Sea and the Aleutian chain, in water cold enough to kill a swimmer in under an hour. It is tempting to file that under courage. That is exactly the wrong reading, and it hides the actual technology. What those crews had was an observation system, not a metaphor. A system with inputs, thresholds, and a decision rule. The inputs were the things you can see from a beach. The period of the swell, meaning the time between crests, which tells you how far away the storm that made it is and how fast it is coming. A change in swell direction, which means the weather system has moved. The color and texture of the water, where a current shears against another current, visible as a line of chop or a slick with a hard edge, sometimes with a line of foam or floating weed marking it. The cloud forms upwind, the behavior of seabirds, which stop working an area before people can feel a reason to. The sound the surf makes on a particular headland at a particular state of tide, which changes days before the weather does. Every one of those is a real physical signal. A swell arriving with a longer period than yesterday genuinely does mean a large distant storm. A current line genuinely is where the water is doing the thing that shortens waves. This was not superstition dressed up. It was pattern recognition applied to variables that professional forecasters now measure with satellites, developed by people whose lives depended on the accuracy, and passed down because the ones who got it wrong did not get to pass anything down. And the output of the system, on most days when the signals were bad, was a single decision. Not today. That is the whole thing. That is the part that got lost. A canoe crew that reads a wrong-looking swell line and stays ashore has used their technology perfectly. Nothing happens. There is no story. The crossing is made 3 days later in flat water. The trade goods arrive. Everybody lives. Success in that system is indistinguishable from an uneventful week, which is exactly why it looks like nothing to an outsider and exactly why it worked. Now put an engine in the boat An engine solves a genuine and enormous problem. Under sail, you go where the wind allows, and a lee shore, land downwind of you, is a death sentence if the wind gets up because you physically cannot claw off it. Engines killed the lee shore. They made schedules possible. They let a ship leave on a Tuesday because the cargo was ready on a Tuesday, cross a strait against the tide, and arrive on time in a headwind. Every one of those is a real gain, and anyone who pretends otherwise has never had to work a sailing vessel off a beach in rising weather. What the engine also did was remove the reason to wait. Once departure stopped depending on the weather, departure started depending on everything else. The charter, the tide window at the far end, the fish quota, the race start, the berth booking, the cruise flights home, the price of the cargo this week versus next week. The decision moved off the beach and into an office, and the person in the office is not looking at the swell line. That is the trade this entire story turns on. Capability went up. The number of situations in which people are exposed to the sea's worst behavior went up faster. You can watch it happen with unusual clarity in one specific piece of water because there is a fleet that crosses it on the same date every single year, whatever the sky is doing. Bass Strait separates the Australian mainland from Tasmania. It is roughly 250 kilometers across and 500 kilometers long, and the number that matters is the depth, an average of about 60 meters with a maximum of around 155. That is not a sea in any meaningful sense. It is a flooded plain. 20,000 years ago, when sea level was lower, you could walk it. 60 meters of water sounds like a lot to a person standing on a dock. To a swell, it is almost nothing. A wave begins to feel the bottom when the water depth drops below about half its wavelength. Southern ocean swell rolling in from the west, generated by gales in the roaring 40s, with 1,000 kilometers of open water to work in, routinely has a wavelength of 200 meters or more. Push that into 60 meters of water, and the wave is dragging. The bottom slows the base while the top keeps going. The wave shortens, steepens, and starts to break in open water with no land anywhere near it. That is the same mechanism as the Agulhas, arriving by a different road. The Agulhas shortens waves with an opposing current. Bass Strait shortens them with a shallow floor. The result on deck is identical. Crests too close together, faces too steep, and a vessel that has not finished recovering from one impact when the next one arrives. Add the funnel. Wind squeezing between the mainland and Tasmania accelerates, and the tidal streams through the strait can run hard, so on any given day, you may also have current against wave on top of the shoaling. Add one more thing that only matters if you know the geography. On the western approach, the seabed climbs from deep southern ocean water onto the shelf relatively abruptly, so the swell does not get a gentle warning. It arrives in shallow water having lost none of its energy. Every serious Australian sailor knows this. It is not obscure. Bass Strait has a reputation among ocean racers that is out of all proportion to its size precisely because it produces short, vicious, breaking seas and weather that would be merely rough somewhere with a deeper bottom. And on 26 December every year, a fleet leaves Sydney Harbour to race across it. The Sydney to Hobart is 628 nautical miles, from a harbour full of spectator boats, down the New South Wales coast, across the strait down the east coast of Tasmania, and up the Derwent. It has run since 1945. It is one of the 3 or 4 races that define an offshore sailing career, and the entry list every year contains professionals, Olympic medalists, and people who have crossed oceans. In 1998, 115 boats started. The forecast at the start was not benign, and nobody pretended it was. North to northeasterly winds of 25 to 35 knots down the New South Wales coast, which is a fast, wet, downwind ride, and exactly what an ocean racer wants. There was a low in the picture. There is often a low in the picture. Crews reefed, checked their storm sails, and went. What developed on 27 December was a small, intense system that formed and deepened over Bass Strait itself, south of Wilson's Promontory, with the central pressure dropping toward 980 hectopascals in a matter of hours. Meteorologists later studied it as a case of mesoscale cyclogenesis, a compact low, spinning up fast, in a place where it could do the most damage. The Bureau of Meteorology upgraded its warnings during the day on the 27th, and by the evening it was a storm warning with forecast winds in the 45 to 55 knot range. On paper, that is a warning. In practice, it arrived with two problems that the coronial inquest afterward examined in detail. The first is arithmetic that most competitors did not know. A forecast wind speed is an average. The Bureau's own convention was that gusts could run around 40% above the forecast mean, and that the maximum wave height in a given sea could substantially exceed the forecast significant wave height. The inquest recorded a figure of 86% or more. So a forecast of 50 knots with a 6-meter sea is, in the fine print, a forecast that includes gusts around 70 knots and individual waves well over 10 meters. The coroner found there was little understanding, and in many cases no awareness at all, of that relationship among competitors and race management. The second problem is geometry again, and it was not in any forecast. 60 meters of water. The waves the fleet met were not the long ocean swell that the numbers implied. They were shortened, stacked, and breaking, with faces steep enough that boats were not rolling over the top of them. They were being thrown. And by the time the storm was unambiguous, the fleet was in the middle of it, and there was nowhere to go. That is the piece people outside sailing get wrong. Racing yachts do not park. In survival conditions, you have three options: run before the sea, lie to a sea anchor or drogue, or heave to. All three require room, and all three assume the sea is regular enough that you can find a rhythm in it. The New South Wales coast was to the west, a lee shore in a westerly gale. Tasmania was ahead. Retreating north meant beating back into it. The shallow water was not a refuge, it was the cause. There was no shallow water shelter, because the shallow water was what was making the waves lethal. 71 boats retired, 44 finished, 5 sank. On Sword of Orion, a fast, competitive boat, the crew had decided to turn back and was heading north when a wave rolled her through 360 degrees. Glyn Charles, a British Olympic sailor who had joined for the race, was in the cockpit, clipped on. The boat went over. The harness attachment gave way, and he went into the water. The crew could see him. They had a boat with a broken mast, no engine that could be used with rigging in the water, and a sea state in which putting another person over the side was a decision to lose 2 people instead of 1. He was never recovered. Business Post Naiad was rolled repeatedly through the night. Bruce Guy, her skipper, died of a heart attack after one of the knockdowns. Phil Skeggs drowned, trapped when the boat went over. The survivors stayed with the hull, in the dark, bailing and waiting, with 2 dead crewmates aboard, until a helicopter reached them the following morning. Winston Churchill was something else entirely. She was a 52-foot wooden yacht built in Hobart in 1942, one of the 9 boats that started the very first Sydney to Hobart in 1945, and probably the most loved vessel in the fleet. On the afternoon of 27 December, she was hit by a wave that opened her up. She sank quickly. 9 men got into 2 life rafts. The rafts separated in the dark. 4 men in one raft were found and lifted out. The other raft, with 5 men, was rolled repeatedly through the night and then flipped hard enough to throw men out of it. John Dean, Jim Lawler, and Michael Bannister died. 2 survivors were recovered the next day, after more than 24 hours in a raft that had stopped being shelter and become something they were fighting to stay inside. That is what killed people in 1998, and it is worth saying plainly, because it is not what the public imagines. Nobody was swallowed by a single monster wave in a moment of drama. The boats were destroyed by repeated impacts from short, steep, breaking seas over hours, and the people died in the gaps. Thrown out of a raft, trapped under a hull, separated by 20 meters of water that could not be crossed. Which brings up the part of this that gets least attention and deserves the most. 55 sailors were pulled out of Bass Strait, most of them by helicopter, in what remains the largest peacetime search and rescue operation in Australian history. Some accounts put the figure at 56. The difference comes from how surface rescues by other yachts and by the Navy are counted. 9 yachts or their life rafts were emptied. Look at what that actually required. A rescue begins with a signal, and the signals were a mess. EPIRBs were activating across 100 miles of ocean. Some boats had them and could not deploy them. Some crews had HF radio contact and some did not. And the relay vessel that had been maintaining the race radio schedule was working through atmospherics and a fleet that was scattering. The coordinating authority, the National Search and Rescue Organization working out of Canberra, had to build a picture of who was where from fragments, while the number of casualties kept growing. Then, the aircraft. Rescue helicopters came from New South Wales Police Aviation, from the Canberra-based service, from Victoria, from the military. Bass Strait is a long way from all of them. A helicopter flying from the mainland to a life raft in the middle of the strait spends a large fraction of its fuel just getting there. And the fuel it burns going out is fuel it cannot spend hovering. That is the constraint that governs everything on scene time. A crew can find a raft and have 20 minutes to work before they must leave or not get home. Now do the work. Winds gusting past 60 knots at sea level, which at rotor height is a machine being shoved sideways constantly. Waves whose crests rise into the hover. Spray and rain reducing visibility to almost nothing at night. And the actual task, putting a paramedic or a rescue crewman on a wire, into that, next to a life raft that is being thrown around, and getting people onto a hook one at a time. Several of those winch operations were performed at night in conditions that the aircrew afterward described in flat, technical language that does not remotely convey them. Crewmen went down the wire into water where the crest-to-trough distance was greater than the length of the yachts they had come from. The people in the rafts were hypothermic, some injured, and a person who has been in cold water for hours cannot grip a strop, which means the rescuer has to do all of it. The rescuers were in exactly the same sea as the people they were pulling out. That is the point. There is no separate safe place from which help arrives. Everyone who came to help entered the identical hazard, in aircraft with a fuel clock running. And the reason more people did not die is that a small number of aircrew and Navy personnel spent that night repeatedly choosing to go back into it. The coroner was critical of the race organizers and of the Bureau. The Cruising Yacht Club of Australia's own review, released on 1 June 1999, produced a long list of changes. Qualifying requirements, radio and safety equipment standards, storm sail rules, harness and tether standards, mandatory training. Ocean racing worldwide changed because of Bass Strait in 1998, and it changed for the better. None of it altered the water depth. And here is the thing that should sit uncomfortably. The forecast was, in its broad shape, correct. A dangerous low was identified. Warnings were issued and upgraded. The information existed and it was transmitted. It simply arrived at a fleet that was already committed. In a strait where the only escape was a coastline they could not safely approach, with a mechanism, shoaling, that no wind forecast describes. Better information does not create sea room. There is something worse in the record than a fleet caught out. And it sits 19 years earlier on the other side of the world. Offshore racing did not learn about shallow water storms in 1998. It had already learned, in the most expensive way available, and had already rewritten its rules once. On 11th August 1979, 303 yachts left Cowes on the Isle of Wight for the Fastnet race, out through the English Channel, west into the western approaches, around the Fastnet Rock off the southwest corner of Ireland, and back to Plymouth. About 3,000 people were sailing. It was, and is, the centerpiece of British offshore racing, and the fleet ranged from full professional crews down to family boats. The water they were racing across is the Celtic Sea, and the relevant fact about it is the same relevant fact as Bass Strait. It is continental shelf. Depths over much of the course run around 100 meters and less. Atlantic swell that has crossed 3,000 kilometers of deep ocean arrives there and climbs onto the shelf. On 13th of August, a depression that had crossed the Atlantic deepened sharply as it moved over the fleet. The wind went to storm force 10, with higher gusts. That is a serious blow, but it is not unheard of in August, and the forecast had it. Late and less severe than what arrived, but it had it. What made it lethal was what the shelf did to the sea. The waves that developed were short, high, and breaking, and they were coming from a direction that was changing fast as the low went through, which meant a confused sea with crests running across each other. A yacht can survive very large waves that are regular. A yacht cannot easily survive waves that arrive from two directions at once because there is no heading that works. Boats were rolled through 360 degrees. Masts came down. Rudders broke. A Royal Air Force Nimrod pilot flying over the area reported wave heights in the region of 50 to 60 feet. 15 competitors died. 5 yachts sank. 24 were abandoned. Only 86 of the 303 starters finished the race. What followed was, at that time, the largest peacetime rescue operation in British history. Something on the order of 4,000 people involved, drawing in RNLI lifeboats from all along the southwest coast and the Irish coast. Royal Navy and Royal Air Force helicopters, the entire Irish Naval Service, a Dutch warship, and any merchant ship in the area that could be diverted. 136 sailors were taken off. Then the inquiry produced the finding that should have changed everything, and it is not the one people remember. The boats mostly did not sink. Read the numbers again. 303 started. 5 sank. 24 were abandoned. And a number of those abandoned yachts were subsequently found still floating. Some of them recovered and sailed again. The hulls, in the main, survived a storm that killed 15 people. The people died in the water and in the life rafts. They died after being swept out of cockpits, after harnesses or their attachment points failed, and after leaving vessels that were damaged, terrifying, half-flooded, and still afloat, for inflatable rafts that came apart, capsized, or lost their occupants. Life raft performance in that storm was, by the inquiry's account, dismal. That is a genuinely counterintuitive conclusion, and it changed offshore doctrine permanently. The rule that came out of it, step up into the life raft, meaning do not leave the yacht until the yacht is physically sinking underneath you, is now taught everywhere, because the 1979 data showed that a crippled hull is a better survival platform than a raft in a breaking sea. The inquiry's overall verdict was blunt, in a way official documents rarely are. The sea had shown it could be a deadly enemy, and people who go to sea for pleasure have to accept they may meet dangers of a very high order. That is close to the sense of it, if not the exact words. Everything then improved. Stability standards for racing yachts were tightened so that boats were required to be more likely to right themselves after a knockdown. Harness and tether standards changed. Life raft design and testing changed. Qualification requirements for crews changed. Radio and safety equipment requirements changed. The sport took the finding seriously and acted on it, and the actions were correct. 19 years later, in Bass Strait, 6 people died, 5 yachts sank, 55 sailors were lifted out. And it happened for the same underlying reason, an intense, low developing over shallow shelf water, producing steep breaking seas from shifting directions, on a fleet with a fixed start date that was already committed and had no accessible shelter. That is the reversal, and it is the most important structural point in this whole story. The reforms after 1979 were not cosmetic and they were not ignored. They worked. Boats in 1998 were tougher, better equipped, and better crewed than boats in 1979, and a smaller proportion of people died. The reforms improved everything about the human response. They could not touch the mechanism because the mechanism is the depth of the water. You can change the boat, the harness, the raft, the radio, the training, and the forecast. The continental shelf stays where it is. And any activity that puts a fleet across shallow water on a date chosen months in advance is, sooner or later, going to meet a low that deepens over that shelf. And the only variable left will be how good the rescue is. So the shallow water gets you when you are far from land. What happens when you are close enough to see the streetlights? Cook Strait sits between two mountainous islands, and that is the whole problem in one sentence. The North Islands Ranges and the Southern Alps stand on either side of a gap about 22 kilometers wide at its narrowest, and every weather system crossing New Zealand has to squeeze through it. Air behaves like water when you constrict it. It accelerates. Wellington is the windiest major city in a country that is not short of wind, and the reason is not local weather. It is the shape of the land upwind. Underneath that, the tide runs. The strait connects the Tasman Sea to the Pacific, and the tidal cycles on the two sides are out of phase. So twice a day a substantial volume of water is pushed through the gap in one direction and then dragged back. The stream can run at several knots. Put a strong tidal stream against a wind-driven sea in a constricted channel, and you get the same compression you get in the Agulhas. On a smaller scale, in a place where a ship has no room to maneuver. At the eastern end of that gap, Wellington Harbor opens through an entrance a little over a kilometer wide, and on the western side of that entrance lies Barrett Reef. On 10 April 1968, two weather systems arrived over Wellington at the same time. One was the remains of a tropical cyclone, Giselle, which had come down from the Coral Sea. The other was a deep low that had come up from the Southern Ocean with a violent southerly behind it. They met over the city. Anemometers on the hills above Wellington recorded gusts in the region of 270 kilometers per hour. The figures quoted in different accounts range from about 260 to 280, and even the conservative end of that is well beyond hurricane force. Roofs came off houses. It remains one of the most destructive storms in New Zealand's recorded history. The inter-Iceland ferry Wahine was approaching the harbor entrance that morning at the end of the overnight run from Lyttelton, with 734 people aboard. She was a modern ship, 10 months in service, with radar and 2 engine rooms. Her master, Hector Robertson, had made this approach many times. The decision to come in was reasonable when it was made. The ship was already committed to the entrance, and turning a large ferry around in a strait in those conditions is not a free action. The plan was to get inside the heads. At around 6:45 in the morning, she struck Barrett Reef. Watch what happens to the options from here, because this is a case study in how a manageable casualty becomes a fatal one without anything dramatic occurring. The grounding damaged her, and she lost steering. That is the first option gone. She can no longer choose where she goes. The wind and the ebb pushed her, and she drifted up into the harbor, dragging. The crew got anchors down off Steeple Rock, inside the entrance, in sight of the city. That is the second option gone. She is now held in one place, in a storm, taking water. She was flooding through the car deck. The mechanical detail that decides everything from this point is dull and unavoidable. A ferry's vehicle deck is one enormous open space with no watertight subdivision, because that is what makes it a ferry. Water that gets onto that deck does not stay put. It runs to the low side as the ship rolls, which pushes the ship further onto that side, which lets more water run to the same side. Naval architects call it the free surface effect. It has no natural stopping point. Once it starts, the ship's own motion does the work. Through the morning, Wahine developed a starboard list, and the list got worse. The order to abandon ship came around 1:30 in the afternoon, roughly 7 hours after the grounding. By then, the list was severe enough that only the starboard lifeboats could be launched. A boat on the high side cannot be swung out over a hull that is leaning away from it, because gravity holds it against the ship. Half her boat capacity was unusable, not because it was damaged, but because of the angle. So most of the people on board went into the water in life jackets, roughly a kilometer from a shoreline they could see. The wind and the outgoing water carried them east across the harbor entrance toward the rocky coast near Eastbourne. And that is where a large share of the deaths happened. Not on the ship, not from drowning in open water, but on the rocks, in a heavy sea in April, among people who were already cold and exhausted, and many of whom were elderly. Reaching land in a storm on a rock shore is not the end of an ordeal. It is a separate event with its own casualty rate. 51 people died that day. The toll is usually given as 53, counting 2 who died later of injuries sustained in the disaster. The rescue was not a state operation with helicopters and cutters. It was Wellington. Tugs went out. The pilot launch went out. Fishing boats and private craft came out into a harbor entrance where the sea was breaking and picked people out of the water one at a time. Residents of Eastbourne climbed down onto the rocks in the wind and pulled people up. Rail workers, off-duty crews, anyone with a boat. The ship capsized onto her starboard side and lay there in the entrance to the capital city's harbor, in daylight for everyone to see. Now count what was available and did not help. The ship had radar. She had radio, and the shore knew exactly where she was the entire time. The harbor was a kilometer away, and the city was a few kilometers beyond that, with a hospital in it. New Zealand's largest concentration of maritime infrastructure was inside the same body of water, and roughly 50 people still died. And that should permanently change how you hear the word nearby. Proximity to land is not proximity to rescue. Rescue is a function of whether a vehicle can physically operate in the conditions between you and help, and in 80-knot winds inside a constricted harbor entrance with a breaking sea. A kilometer of water is an obstacle no different in kind from 100 miles of it. The tugs could not go alongside a listing ship in that. The launches could take people out of the water only where the sea let them. The helicopters of 1968 in that wind were not an option at all. There is a second lesson buried in the timeline that most retellings skip. 7 hours passed between the grounding and the abandoned ship order. That is not incompetence. The ship was anchored inside the harbor, and the reasonable expectation was that the weather would ease and she could be secured. The decision to hold was defensible right up until it wasn't. What changed was not the storm. It was the angle of the deck. The list did not announce itself. It accumulated degree by degree while everyone waited for conditions that never improved. And by the time the situation was unambiguous, half the lifeboats had already been taken out of service by the ship's own attitude. Nobody has ever recorded the exact moment a list becomes unrecoverable. You find out afterward. Hold on to that, because it is going to happen again. On a structure enormously larger and more sophisticated, in water so cold that going into it is not an option at all. And there will be no shoreline to be carried toward. The Grand Banks lie southeast of Newfoundland, and they are, once again, shallow. Over a huge area, the water is between about 25 and 100 meters deep, a submerged plateau sticking out into the North Atlantic. That shallowness is why the fishing was, for 4 centuries, the best in the world. Sunlight reaches the bottom, nutrients get stirred up, and the cold Labrador current meets the warm Gulf Stream right there and mixes everything. Those same 2 currents produce the fog. Warm, moist air over the Gulf Stream slides north over the cold Labrador water. The moisture in it condenses, and the banks disappear inside a white ceiling that can sit there for days. The Labrador Current also brings the icebergs down from Greenland, past the same waters where the Titanic went, which is not a coincidence of geography so much as the whole point of that geography. And a North Atlantic winter storm crossing that plateau does to swell exactly what Bass Strait does to it. The bottom is close, the waves shorten and steepen and break. In February 1982, there were 3 large drilling rigs working the Hibernia field, roughly 315 kilometers east-southeast of St. John's. The biggest was the Ocean Ranger. She was a semi-submersible, an enormous platform sitting on 2 submerged pontoons, with the working deck held high above the waves on columns. The design exists to solve the wave problem. Put the buoyancy deep enough, and the surface can do what it likes. The platform barely moves. The Ocean Ranger was the largest semi-submersible in the world when she was built in 1976, and she had been described as capable of drilling anywhere. She was rated for the worst sea state the North Atlantic could produce. 84 men were aboard. On the night of 14th of February, a severe storm crossed the banks. Winds around 100 knots. Waves in the region of 15 to 20 meters. Bad, even for there. And the rigs did what rigs do. Shut down drilling, secure everything, and ride it out. That is what a semi-submersible is for. At some point in the evening, a wave broke a port light, a glass window, in the ballast control room. Read that again and hold it against the size of the thing. The ballast control room was the compartment from which the platform's stability was managed, and it had a window in it. At a height the sea was able to reach in a storm, the platform was rated to survive. Seawater came through onto the ballast control panel. The panel was an electrical console that operated the valves letting water in and out of the pontoons and columns, which is how a semi-submersible keeps itself level. With salt water in it, the panel began doing things nobody had commanded. Valves opened and closed on their own. Crew members later reported to the other rigs by radio that the panel was malfunctioning and that they had shut off its power. That was a sound instinct, and it created the next problem. With the panel dead, the valves froze wherever they happened to be. To move ballast now, someone had to go out to the valves themselves and work them by hand, using brass rods designed for exactly this contingency. Manual override is only useful if the people holding the rods know exactly what the system is doing. The Royal Commission that examined this afterward concluded the crew did not fully understand the ballast system's behavior in an emergency and had not been trained for it. Water went into the wrong tanks. The platform began to settle by the bow. Now the geometry turns against them, and this is the thread that connects a drilling rig to a ferry in Wellington Harbor. A semi-submersible is stable within a range of trim. Tilt it far enough forward, and the chain lockers, which the Commission found were not watertight, start taking water, and the buoyancy that was holding the bow up starts disappearing. Like Wahin's car deck, it is a process that accelerates itself. There is no plateau. At around 1:10 in the morning on 15th of February, the Ocean Ranger began transmitting Mayday. The last radio message received from her at about 1:30 reported that the crew were going to lifeboat stations. On that night, those words meant something very specific. The standby vessel, the supply boat Seaforth Highlander, was nearby. Other rigs were within radio range. Helicopters existed, and none of it mattered, because in 100-knot wind, with 20-meter seas, a helicopter cannot hover over a listing platform, and a supply vessel cannot come alongside one without being destroyed against it. The rescue assets were present and physically unable to perform a rescue. What they could do was wait for men to come to them through the water. At about 2:20, the Seaforth Highlander sighted flares and found a lifeboat with men in it, damaged, in the sea. Her crew got a line across. They tried to haul the boat in. The line parted. The lifeboat was overwhelmed and capsized, and the men went into the water. The water temperature was around -2 degrees Celsius. Nobody aboard the Ocean Ranger had an immersion suit. In water that cold, without one, a person has minutes of useful function. Hands stop working almost immediately, which means you cannot grab a rope, even if one lands across you. The Seaforth Highlander had no equipment designed to lift unconscious people out of the sea. Her crew watched men in the water a few meters away and could not get them aboard. All 84 died. 22 bodies were recovered. Post-mortem examination concluded they had drowned while hypothermic. The same storm was still working. 65 miles to the east, the Soviet container ship Mechanic Tarasov was in trouble. Her cargo had shifted on the afternoon of the 15th. Containers punctured a ballast tank, and she took a list. She sank early on 16th of February, about 390 kilometers east of Newfoundland. 5 of her 37 crew were pulled out by an Icelandic vessel. 32 died. 2 vessels, roughly a day apart, one weather system, and the same underlying failure in both. A list that started small, fed on itself, and could not be stopped from inside. The Royal Commission on the Ocean Ranger Marine Disaster, chaired by Chief Justice T. Alex Hickman and reporting in 1984, was unusually direct. The rig had design flaws. The port light, the non-watertight chain lockers, a ballast control system that could be disabled by seawater. The crew were not adequately trained for a ballast emergency. There were no survival suits. The lifeboat arrangements were not suitable for those conditions. And the regulatory bodies in both Canada and the United States had been ineffective at inspection and oversight. The changes that followed were real. Immersion suits and survival training became mandatory on Canadian offshore installations. Standby vessels got equipment for recovering people from the water. Offshore regulation in Canada was restructured, and the loss is still taught in engineering schools as a case study in how a small breach propagates into total loss. Every one of those fixes addressed the second half of the chain. What happens after the platform is doomed? None of them addressed the first half. The bleak part is not that the sea was too strong. The Ocean Ranger did not fail because the sea exceeded her design. She failed because a window broke and the water got into the one room that controlled her balance. The strongest structure on the Grand Banks was defeated by an opening the size of a dinner plate and a control panel that could not tolerate being wet. Almost exactly a year later, far down the same coast, a ship went down in water shallow enough to stand a building in, and exposed a hole in the rescue system that nobody had thought to look for. The coast between the Chesapeake and Cape Lookout has been called the graveyard of the Atlantic for 2 centuries, and the reason is a piece of geography that sits at Cape Hatteras. The warm Gulf Stream runs north along that coast. Cold water runs south to meet it. They collide right at the Cape, and where they collide, the sea has built the Diamond Shoals, shifting banks of sand that reach roughly 8 miles offshore, moving constantly, with deep water on either side. Warm current against cold current means fog with no warning. Warm water under cold air in winter means storms that intensify as they come off the land and hit the Gulf Stream. Shifting shoals mean a chart that is out of date faster than it can be printed. And the coastal shipping route runs straight past all of it, because going around adds a day. Estimates of the wrecks in that stretch vary depending on where you draw the boundary and how far back you count. Figures from around 600 on the shoals themselves up to several thousand along the wider coast appear in the record. The exact number is not the point. The point is that it is a shallow, current-torn, fog-prone shipping corridor that has been taking ships since the 16th century and still does. On the night of 11 February 1983, the collier Marine Electric was working north up that coast in a full gale, carrying coal from Norfolk toward Massachusetts. She was 605 feet long, and she was old. A Second World War hull, converted and lengthened, with hatch covers that had been patched over the years, and a maintenance record that would become the central issue in everything that followed. She was not, that night, minding her own business. A small fishing boat, the Theodora, was in trouble nearby. The Marine Electric was diverted to stand by her, and she did, staying with the fishing boat in a gale for hours, until a Coast Guard cutter could take over. That was the correct thing to do, and her master did it. By the time she was released and resumed her passage, she had spent the night working in heavy seas, and her bow was going down. Water was getting into the forward holds. The hatch covers, which are the only thing between the sea and a hold on a ship like that, were not holding. She got heavy forward, and a ship that is heavy forward stops rising to the waves. She starts driving through them instead, which puts more water on deck, which gets into the holds, which makes her heavier forward. The same self-feeding curve as the Wahin's car deck, the same as the Ocean Ranger's trim. In the early hours of 12th of February, about 30 miles off Chincoteague, Virginia, the Marine Electric rolled over and sank. The water there is around 120 feet deep. She sank in less water than her own length. 34 men went into the Atlantic in February. The sea temperature was a few degrees above freezing. They had life jackets, and they had a lifeboat that could not be launched properly, and they had no immersion suits because immersion suits were not required. 3 men survived. 31 died. Now the rescue, and this is why this incident belongs here rather than in a list of shipwrecks. The Coast Guard responded fast. Helicopters were overhead while men were still alive in the water. The crews could see them. And in 1983, a Coast Guard helicopter crew had exactly one tool for a person in the water: lower a rescue basket on a cable and hope the person can get into it. A man who has been in water a few degrees above freezing for half an hour cannot get into a basket. His hands have stopped closing. He cannot grip. He cannot pull. He cannot lift his own weight. He is conscious, he can see the aircraft, and he is physically incapable of participating in his own rescue. The United States Coast Guard did not have rescue swimmers. There was nobody aboard those aircraft whose job was to go into the water and put a person into the sling. The helicopters hovered over men they could not pick up. 3 survivors came out of it. One of them, the chief mate, Bob Cusick, who spent hours in the water and lived. His testimony to the Coast Guard's Marine Board is what opened the case, because he could describe the condition of the hatch covers from the inside. The investigation that followed was brutal for everyone involved. It established that the ship's hatch covers and deck plating were in a condition that should have taken her out of service, and that the inspection regime, both the Coast Guards and the classification societies, had passed her anyway. It became one of the most consequential marine casualties in American history, and the reason is what came out of it. Immersion suits became mandatory for American merchant crews working cold water routes. The same fix Canada had just made offshore, arriving in the merchant fleet a year late and 31 men too late. Inspection standards for aging vessels were tightened, and a substantial number of Second World War-era hulls left service rather than face the new regime. And the Coast Guard established a rescue swimmer program. That is the change that matters most, and it is worth being precise about what it fixed. Every other reform so far has addressed prevention. Better hulls, better forecasts, better stability rules, and every one of them can be defeated by a bad enough day. The rescue swimmer addressed the last 5 meters. It accepted that people would end up in the water unable to help themselves, and it put a trained human being on the end of the cable to close the gap. Since then, Coast Guard rescue swimmers have gone into the water in conditions that the aircraft commanders describe in careful, unexcited language, and they have taken people out who could not have been taken out any other way. It is the single most effective thing anyone in this entire story ever did about the problem, and it exists because 31 men drowned in 120 feet of water while help hovered overhead. Note what it does not do. It does not shorten distance. A swimmer is only useful where a helicopter can be. Rally remains is huskar, and a helicopter's usefulness is bounded by range, fuel, weather, and the simple fact that hovering in violent air is a controlled emergency that a crew can only sustain for so long. Which brings up a question that gets much worse the further north you go, into water so cold that time in it is measured in minutes rather than hours. What if the sea does not break anything at all, and the vessel is gone before anyone knows to launch? Go north from the Grand Banks in your head and cross to the other side of the continent, into the eastern Bering Sea, and you find the same shape of seafloor doing the same job. The eastern Bering Shelf is a vast, shallow plain, much of it 50 to 70 meters deep, running from the Alaska Peninsula up toward the Bering Strait. And like the Grand Banks, it is fabulously productive, and it makes short, hard seas out of ordinary weather. The Bering has a second weapon that none of the places so far have needed. Seawater freezes at about minus 1.8 degrees Celsius. Air over the Bering in February is regularly minus 10, minus 15, colder. So you have a sea that is liquid, and an atmosphere that is well below freezing, and between them, a vessel throwing spray. Every time a bow drops into a wave, water is flung into the air. Wind carries it aft across the boat as a fine, dense mist. It lands on steel that is already at air temperature, that is well below freezing, and it freezes on contact, not in sheets, in layers, thin ones, repeatedly, wave after wave, for hours. The ice does not go where you would want it. It goes where the spray reaches, the rails, the rigging, the mast, the antennas, the wheelhouse front, the crane, and above all the gear stacked on deck. It builds fastest on thin things with lots of surface area, and a stack of steel crab pots. Open frames of bar and mesh, 7 feet on a side, is about as close to a perfect ice collector as anyone has ever accidentally built. A pot that weighs 700 pounds dry can take on hundreds of pounds of ice. Multiply by a deck load of them. What that does is the quietest killing mechanism anywhere in this account. A boat floats upright because its weight is concentrated low and its buoyancy pushes up from the sides. Roll it, and the hull's shape creates a righting force that shoves it back. Add weight high, on the rails, on the mast, on top of a pot stack, and you have raised the center of gravity. The righting force gets weaker. The boat still comes back upright, just more slowly, and with less enthusiasm each hour. Nothing breaks, no alarm sounds. There is no gauge on any boat that reads out remaining stability. The only symptom is that the vessel feels sluggish in the roll, and the crew, who are hammering ice off the rails with baseball bats and mallets, in the dark, on a pitching steel deck, in wind chill that freezes their clothing stiff, are too busy to notice a change measured in fractions of a second of roll period. At some point on that curve, the boat stops being able to come back at all. There is no warning line. It happens once. That is what happened to the Destination. She was a 98-foot crab boat with a long history in the fishery, and in February 2017 she was working the Opilio season, snow crab, on the shelf, in the worst month of the year. That timing is not bravado. The Bering Sea crab fisheries operate on quota shares, with a season, a delivery schedule, and processing plants that have to be fed. The crab are there in winter. The market is there in winter. The alternative to fishing in February is not fishing in a nicer month. It is not fishing. She left Kodiak, stopped at Dutch Harbor, and headed northwest for St. Paul in the Pribilof Islands with her pots stacked on deck, bait aboard, and full fuel. 6 men: Jeff Hathaway, Larry O'Grady, Charles Glenn Jones, Raymond Vinsler, Kai Hammock, and Derek Seibold. The National Weather Service had a heavy freezing spray warning out. It was not ambiguous, and it was not missed. Freezing spray warnings in the Bering in February are routine, which is exactly the problem with them. A warning that is issued constantly stops functioning as information and becomes background. Boats fish through them. Boats have always fished through them. The practice is to work the ice down as it forms and keep going. On the morning of 11th February, the Destination was in the lee of St. George Island, which is a real tactic and a good one. Put a piece of land between yourself and the wind, and the spray stops. Behind an island, a boat can go hours without taking on ice, and the crew can get ahead of what is already there. At about 6:10 in the morning, she rounded Danoy Point and came out of the lee. Beyond the point, the wind was northeast at 20 to 30 knots, and the seas were 8 to 14 feet. Read those numbers as a fisherman would. That is nothing. That is an ordinary working day in the Bering, whether that boat had operated in 1,000 times. If you were writing a forecast, you would not underline it. Within moments, the vessel pivoted 256 degrees to starboard as her speed fell below 2 knots. She capsized. The NTSB estimated she was gone in roughly 4 minutes. No mayday was ever transmitted. Not a word. The emergency beacon activated automatically at about 6:15 as the boat went under, and the first anyone ashore knew of it was a satellite alert. The Coast Guard responded to that beacon with aircraft, and by the time they were overhead, there was a debris field, buoys, tarps, an oil sheen, a life ring with the boat's name on it, 2.5 miles northwest of St. George Island. The search ran across thousands of square miles for about a day. Nobody was found. All 6 men were lost. The National Transportation Safety Board's report, issued in 2018, found the probable cause to be the captain's decision to continue into heavy freezing spray conditions without ensuring the vessel retained a margin of stability sufficient to absorb the ice. Contributing factors included the vessel being loaded beyond what her stability guidance allowed once the gear, bait, and fuel were counted, and a regulatory framework in which a vessel of that class was required to have stability instructions, but not in practice, to obtain a predate corrections tolerance to demonstrate compliance with them on any given trip. Now hold that against the Ocean Ranger, because the contrast is the point. The Ocean Ranger died from a breach. A window broke, water got in, a system failed, and a chain of events unfolded over roughly 6 hours during which people knew something was wrong, made decisions, transmitted, and mustered. The destination died with nothing broken, no hull damage, no flooding, no failure of any component. Every system aboard was working normally at the moment she went over. What had changed was a number that nobody can see, the height of the center of gravity. And it changed by accumulation, from spray, in weather that would not make the news. That is the new thing this proves. And it is the most unsettling proposition so far. A vessel can be lost by a process that produces no symptom the crew can act on, in conditions they have every reason to consider routine, and be gone before a radio call is possible. The men aboard were not passive, and they were not reckless. Crews in that fishery beat ice for hours on end because that is what you do. The destination had used the lee of the island, which is the correct move. The failure was that the accumulated ice had already spent the margin, and the moment of exposure that used up the last of it was indistinguishable from 100 previous moments that had not. So the question becomes how far away help is, and in the Bering that number is the whole story. Coast Guard Air Station Kodiak covers the Alaskan waters, and Kodiak to the middle of the eastern Bering Shelf is a very long flight. The service knows this, so during the winter crab and trawl seasons, it forward deploys helicopters, putting a Jayhawk and its crew out at Cold Bay, or on St. Paul in the Pribilofs, hundreds of miles closer to where the fleet is working. That is a deliberate, as a expensive decision to buy time. And it is the difference between a 2-hour response and a 5-hour one. Even forward deployed, the geometry is unforgiving. A helicopter has a radius of action, and the radius shrinks with headwind, and shrinks again with the fuel it must reserve to hover. In February, in the dark, in icing conditions that affect aircraft the same way they affect boats, that radius is not a circle on a chart, it is a negotiation. And in water at or near freezing, a person in an immersion suit has maybe a few hours. Without one, minutes. On 23rd of March 2008, the system got its best possible test. The Alaska Ranger was a head and gut trawler, a factory vessel that catches fish and processes them aboard, working about 120 nautical miles west of Dutch Harbor. She had 47 people aboard. A large crew because processing is labor. In the early hours of the morning, she began flooding aft. The National Transportation Safety Board later determined that the triggering event was most likely the loss of one of her two rudders, which left an opening, a rudder trunk about 9 inches across, through which the sea came in. That alone should not sink a ship of that size. What sank her was that the flooding did not stay in the rudder room. Watertight integrity inside the hull was inadequate, and the water spread compartment to compartment until she went down by the stern. Here is what went right, and it is almost everything. They knew. The flooding was detected, the crew had time, and the master got a distress call out. People got into immersion suits. Actual suits on almost everyone because by 2008 that was law, and the law existed because of the marine electric. The crew abandoned into life rafts and into the water in an orderly way. A sister ship, the Alaska Warrior, was in the area and came to them. A Coast Guard Jayhawk was forward deployed at St. Paul and launched. A Dolphin helicopter operating from the cutter Monroe joined. A C-130 flew overhead to coordinate, because at that distance from anywhere, radio relay is a service somebody has to physically provide by circling in the sky. 42 people were pulled out of the Bering Sea that night, by helicopter hoist and by the Warrior's crew. 5 died, including the captain, the chief engineer, and the mate. That is the ceiling. Everything that can go right did go right. Warning, suits, rafts, a nearby ship, aircraft within range, a coordination platform overhead, competent execution under lights in 20-foot seas. And 5 people still died in a rescue that is taught as one of the most successful in Coast Guard history. Set that next to the destination, and you have the two ends of the same problem. The Alaska Ranger's crew had a mechanical failure they could detect, half an hour to act, and suits. The destination's crew had a stability margin that had been silently spent by ice, 4 minutes, and no transmission at all. The best rescue apparatus in the world was, in the second case, entirely irrelevant, because the event was over before any part of it could be told. There was an event. That is the limit of a rescue service, stated as plainly as it can be stated. Rescue is a response to information. Where the failure produces no information until after it has happened, response is not a strategy. So the honest reading of the Bering is not that people there are underserved. They are served about as well as physics allows. The forward deployments, the suits, the beacons, the swimmers, the C-130 overhead. That is a serious, expensive, functioning system, and it has saved a lot of people who would otherwise be dead. It is also a system that spends most of its effort covering distance, and distance is the one variable that no amount of money changes. You can make the helicopter faster, you cannot make the Bering smaller, unless you put the station on the beach at the exact point where the danger is and wait there. There is a place that ran that experiment. The Columbia River drains an area larger than France, and all of it comes out through one gap about 5 kilometers wide, between Cape Disappointment in Washington and Point Adams in Oregon. Outside that gap, the river's sediment has built a shoal, the Bar, roughly 3 miles across, reaching about 6 miles out into the Pacific. Everything that makes the other places on this list dangerous is present here, compressed into an area you could drive across in 10 minutes. The North Pacific throws swell at that coast all winter, generated by storms in the Gulf of Alaska with thousands of kilometers of fetch. That swell arrives in deep water and then runs up onto the Bar, where the depth drops away to a fraction of what it was. Shoaling, the Bass Strait mechanism, turns it short and steep immediately. On top of that, the river is coming the other way. On the ebb, the outflow of the Columbia runs seaward at several knots, and in spring, when snowmelt has the river up, the freshwater plume can extend 100 miles offshore. Current against swell, the Agulhas mechanism, shortens and steepens the waves further. Both mechanisms, in the same water, at the same time, in a channel narrow enough that you cannot go around. The result is a place where the sea can be flat outside and unrecognizable an hour later on the same tide. Breakers on the bar reach 40 feet in winter and have been recorded higher. Ships wait days, sometimes a week, for the bar to be crossable. The Columbia River Bar pilots board incoming vessels offshore and take them across because no captain unfamiliar with it is allowed to try. The Army Corps of Engineers built jetties in 1885 and 1917 to control the channel, and the jetties helped navigation and did nothing about the physics. Since 1792, the bar has taken more than 2,000 vessels and roughly 700 lives. The wider stretch of coast it belongs to is called the Graveyard of the Pacific, and unlike most such names, it is not a tourism invention. So the United States put a life-saving station on the beach, 2 of them, one on each side, Cape Disappointment to the north, Point Adams to the south, with boats and crews whose entire job is to go out onto that bar when something goes wrong on it. On 12th of January 1961, something went wrong. The Mermaid was a small crab boat with 2 brothers aboard, Bert and Stanley Bergman. In the afternoon, her rudder broke near the bar. That is a mundane mechanical failure. On a lake, it is an inconvenience. On the Columbia Bar in January, with an ebb running, a boat that cannot steer is a boat that will be taken by the current into the breakers and rolled. The Bergmans got a radio call out. That is the whole system working as designed. A mechanical failure, immediate communication, a rescue station a few miles away, daylight remaining. Cape Disappointment launched a 40-foot lifeboat and a 36-footer. The 40-footer found the Mermaid near the entrance buoy and got a tow line on her. Point Adams launched the Triumph, a 52-foot motor lifeboat, the biggest and most capable boat available, and she took over the tow. Watch how a rescue turns into a casualty. Towing a disabled vessel across a bar means the 2 boats are physically connected, which removes the rescue boat's freedom to maneuver. She can no longer choose her angle to a breaking sea because she is tied to a dead weight astern that has to follow. Every coxswain on that coast knows this. It is also the only way to get a boat with no rudder off the bar, so the trade-off gets made. A heavy breaker came through and parted the tow line. The Mermaid went adrift. The same sea capsized the Triumph. 52 feet of purpose-built rescue boat. And she went over. What followed was a series of attempts by men in small boats to pull other men out of a bar in a winter night. A second lifeboat capsized. The 36-footer stayed upright, picked men out of the water, and ran them to the lightship Columbia moored offshore. One man from the Triumph, thrown clear, was carried by the surf and washed ashore alive on the spit. The Mermaid, taken in tow again by a Coast Guard cutter, was lost when that tow parted as well. 7 men died. 5 of them were Coast Guardsmen who had gone out to help 2 fishermen. The 2 fishermen died too. That is the arithmetic that sets this incident apart from everything else here. Everywhere else, rescue was limited by distance, by fuel, by weather, by a helicopter's inability to hover. Here, the rescue capacity was 3 miles away, launched immediately, crewed by professionals, in the boat designed for exactly this. And the bar consumed it. More rescuers died than victims. Rescue capacity is not a fixed resource sitting in reserve. It is a thing you spend, and the environment gets a vote on how much it costs. The Coast Guard's response is the most instructive part, and it is the one genuine piece of good news in this entire story, so it deserves to be told properly. They did not conclude that the bar needed better forecasting. Forecasting would not have helped. Everyone knew the bar was breaking. They did not conclude that crews needed to be braver. They concluded that the boat had to be able to capsize without dying. The 44-foot motor lifeboat was designed in 1961 and built from 1963. It was self-righting and self-bailing. Roll it upside down and it comes back up on its own. And during trials at Curtis Bay, the prototype righted itself in about 3 seconds. Water that comes aboard drains out by itself. The engines are arranged so they keep running through the roll. The crew are strapped in. That changes the meaning of the word capsize. On the Triumph, capsizing was the end. On a 44 and on the 47-foot motor lifeboat that replaced it starting in 1997, which self-rights in under 10 seconds with all systems still functional. Capsizing is an event you get through and then continue working. In 1968, the Coast Guard established the National Motor Lifeboat School at Cape Disappointment, on the bar itself. Because if you are going to train people to operate in breaking surf, you have to take them into breaking surf. Crews come from all over the country to run boats through the same water that killed the Triumph's people, deliberately, in winter, as coursework. Here is the reversal, and it is the most useful idea in this story. Everywhere else on this coast, the answer to a lethal environment had been to predict it, avoid it, or build something big enough to ignore it. All 3 of those had failed repeatedly. The Columbia Bar produced a different answer: accept that the sea will win the encounter, and build a machine and a crew that survive losing. That works. It works because a lifeboat is small, cheap, and expendable in a way a container ship is not, and because its mission is measured in hours, not weeks. Scale that answer up, and it collapses. You cannot build a self-righting bulk carrier. You cannot roll a drilling rig and continue. And the moment the mission gets longer than a few hours, and further from shore than a few miles, you are back to the older arrangement, in which survival depends on knowing what the weather is going to do and getting out of its way in time. And the bulk carrier is the case that proves it, because for about 20 years, the world quietly lost them at a rate that would have caused a public emergency in any other industry. Through the 1970s and 1980s, large dry cargo ships, the ships that move ore, coal, and grain, the least glamorous and most numerous heavy vessels afloat, were disappearing. Not sinking slowly after a collision. Disappearing, often with all hands, sometimes without a distress call. Over that period, the loss rate ran at something close to 1 ship every few weeks. The crews were mostly from countries whose seafarers do not generate headlines, the cargoes were commodities, and the ships were owned through structures that made accountability diffuse. It took a very long time for anyone to treat the pattern as a pattern. The ship that finally forced it was British, enormous, and famous. The Derbyshire was an oil bulk ore carrier of around 90,000 tons, the largest British registered ship ever lost. In September 1980, she was in the Western Pacific, off Okinawa, carrying iron ore, when she went into Typhoon Orchid. On 9th September, she sank. 44 people died, 42 crew and 2 wives who were aboard. There was no distress call that established anything, no survivors, and for 14 years, no wreck. The original inquiry could say only that she had been lost in a typhoon, which is a description rather than an explanation, and the families were left with an official position that came uncomfortably close to blaming the ship's builders, or the weather, or nothing at all. What broke it open was persistence. The families and the seafarers' unions kept pushing, and in 1994, an expedition funded by the International Transport Workers Federation found the wreck. Further surveys in the following years, funded by the British government and the European Commission, went over it in detail with remotely operated vehicles, collecting tens of thousands of images of a ship lying in over 4,000 meters of water. The reopened formal investigation reported in 2000, and the sequence it reconstructed is the reason this case matters here. The failure did not start at the hatches over the cargo holds. It started at the very front of the ship, at the small structures on the foredeck. Ventilators and the hatch to the forward store were damaged and lost to wave impact. Water began entering the bow spaces. That is a leak into a compartment that carries no cargo and is not, on paper, critical. What it does is put weight in the very front of the ship. The bow sits lower. A bow that sits lower stops lifting to the oncoming sea and starts being buried by it, so the waves that used to pass under the ship now break green across the foredeck, at full force, directly onto the number 1 hatch cover. Hatch covers are designed for a pressure load. They are not designed to be hit repeatedly by a moving wall of water. When number 1 went, the hold beneath it flooded, which put the bow lower still, which put more water onto number 2. The investigation described a progressive failure running aft along the ship, hatch by hatch, each one exposed harder than the last, until the vessel had no buoyancy forward and drove under. The whole thing would have taken minutes, at night, in a typhoon, with the crew almost certainly unaware that anything had begun until it was finished. Read that chain against everything that came before it, because it is the same chain every time. A small opening. Water where it does not belong. A change in the vessel's attitude. The change in attitude increases the loading that caused it, and a process that a crew could have stopped at the start becomes one they cannot stop at all, not through error, but because the ship's own geometry has turned against them. The Waheen's car deck, the Ocean Ranger's forward trim, the Marine Electric's bow, El Faro's list, which is coming, the destination's rising center of gravity. The mechanism differs. The shape of the curve does not. The consequences of the Derbyshire investigation were substantial and technical, which is why almost nobody outside the industry knows about them. Classification societies rewrote the rules for bulk carrier hatch covers and forward structures, requiring them to withstand far higher wave loads. Requirements came in for water ingress alarms in forward spaces, so that a crew would at least know the bow was filling. Survey regimes for aging bulk carriers were tightened. The loss rate fell. That is a genuine victory, and it should be counted as one. It is also worth noticing what kind of victory it was. It took a 20-year loss pattern, a 14-year search, a campaign by bereaved families, a national government, the European Commission, several deep ocean survey expeditions, and a reopened public inquiry to establish that ventilators on a foredeck needed to be stronger. The system is capable of learning. It learns at the speed of institutions, and the ocean does not, which leaves one last defense, the one everything modern rests on. If you cannot outbuild the sea, you avoid it. You know where the storm is, and you go somewhere else. By the 21st century, that was supposed to be a solved problem. On the evening of 29 September 2015, the cargo ship El Faro left Jacksonville, Florida, for San Juan, Puerto Rico. She was 241 meters long, American-flagged, steam-driven, built in 1975 and converted over the years to carry containers on deck and vehicles and trailers below. She ran a scheduled service, the same route week after week, carrying a substantial share of the goods that keep Puerto Rico supplied. 33 people were aboard, 28 crew, and 5 Polish contract workers doing a refit job while the ship worked. Out in the Atlantic, there was a system called Joaquin. Consider what that bridge had available, because it is the entire point of this part of the story. Satellite communications, email, radar, GPS. The National Hurricane Center's advisories arriving automatically over the ship's safety terminal. A commercial forecasting product called the Bon Voyage system, which delivered graphical weather packages showing the storm's projected track laid over the ship's route so an officer could look at a screen and see where the hurricane would be when the ship got there. That is more meteorological information than any master in history had until about 20 years ago. It is more than the 1998 Sydney to Hobart fleet had. It is incomparably more than the Waratah had. And here is how it failed. The BVS packages came in by email, and they were not live. Each one was built from a forecast issued some hours earlier, then transmitted, then downloaded when the ship's system pulled its mail. By the time an officer looked at a package on the screen, the information in it could be 6 hours old or more, sometimes considerably more. That does not matter when a storm is behaving. It matters enormously when a storm is not. Joaquin was not behaving. The early forecasts had it recurving north before it reached the Bahamas. The normal thing for a system in that position. Instead, it tracked southwest and intensified, and it did so faster than the forecast guidance was keeping up with. The National Hurricane Center advisories arriving on the ship's safety terminal were more current than the BVS graphics. The two sources did not agree, and the disagreement was the single most important piece of information on that bridge. The NTSB found that the captain, Michael Davidson, did not use the most current weather information available to him, and that his actions to avoid the hurricane were insufficient. He was working from a picture in which the storm went north. That is not the whole of it, and the rest is where it stops being a story about one man. There were officers on that bridge who were uneasy. The voyage data recorder, and this is the extraordinary part of this case, captured 26 hours of bridge audio, so this is not reconstruction. Watch officers raise the idea of diverting south, of taking the old Bahama Channel, which runs in the lee of Cuba, and would have put a lot of land between the ship and the weather. The captain's plan was to continue on the direct route and use the alternate channel on the way back. Suggestions were made and not adopted. The board described the bridge resource management as ineffective, including the captain's failure to adequately consider his officers' input. Underneath that sat a commercial reality nobody on the ship invented. The service ran on a schedule. A diversion costs fuel and hours, and the ship carried freight that Puerto Rico needed on a particular day. The company had a shoreside operation that could have been more actively involved in the routing decision and was not. By the small hours of 1st October, El Faro was close to Joaquin's center in hurricane conditions. Now the ship's own condition starts to matter, and it comes down to details a passenger would never notice. She had a scuttle, an access hatch, on the second deck that was found to have been left open, and water was getting into cargo hold 3. Vehicles down below broke loose. Water on a vehicle deck does what it did on the Joaquin. It runs to the low side and stays there, and the ship leans further, and more comes in. El Faro took on a list to port, and the list did something to the engine that almost nobody outside the machinery spaces would predict. She was steam-driven, with a lubricating oil system that fed the main propulsion turbine and its reduction gear from a sump. That sump has an intake, and the intake sits at a place that assumes the ship is more or less upright. Lean the hull far enough, and the oil in the sump moves away from the pickup. Pressure falls. Once lube oil pressure to a main propulsion unit drops below a set point, the plant trips, because running a turbine and gearing without oil destroys them in seconds. At around 6 in the morning, El Faro lost propulsion. Understand what that removes. A ship with power can steer, and steering is survival. You point the bow into the sea so the waves hit the strongest part of the hull, and the ship rides them. A ship without propulsion cannot hold a heading. She falls off, turns broadside, and takes the sea on the beam, the worst possible angle, the one that rolls vessels. The engineers worked the problem. They could not restore power, because the fix for the oil supply was to reduce the list, and the fix for the list was the propulsion they no longer had. That is a closed loop, and it is the point of no return in this incident. The objective stopped being San Juan. It stopped being the ship. At around 7:15, the captain reported the situation ashore, and the emergency went into the system. The abandoned ship order came a few minutes later. The board found the decision to muster the crew came late, that the time between the ship becoming unsurvivable and the order to leave her was too short for what leaving her required. And leaving her required a lot. El Faro carried open lifeboats, the old kind without a roof, launched on davits over the side, which were legal for a ship of her build date under grandfathered rules, and which are useless in hurricane conditions because you cannot lower a boat down the side of a rolling hull into a sea like that. The crew's realistic option was immersion suits and life rafts. Now the rescue, in the order it actually happened, which is the order these things always happen in, and the one that never appears in dramatizations. Recognition came from the ship, by satellite, and it was current. The Coast Guard knew there was a ship in distress and knew roughly where. Assets existed, aircraft in Florida, cutters, commercial vessels that could be diverted. None of it could get there. A Category 3 hurricane sat between the searchers and the search area. Fixed-wing aircraft could not usefully operate in it. Helicopters certainly could not. Surface vessels could not close the position. Every element of the modern rescue chain, detection, communication, authorization, launch, worked exactly as designed, and then stopped at the physical wall, which is that no aircraft or vessel could be in that airspace or that water. The searching began as the storm moved off. What they found over the following days was a debris field, an oil sheen, containers, a damaged and empty lifeboat, and a single body in an immersion suit. All 33 were lost. The wreck was located on 31st through October 2015 by the Navy salvage ship USNS Apache in roughly 4,600 meters of water, standing upright on the bottom with the navigation bridge structure torn away and lying separately. In August 2016, after an operation that had to be attempted more than once, the voyage data recorder was recovered from that depth, one of the deepest such recoveries ever performed, and it still worked. That is why this case stands apart from all the others. The El Faro's last 26 hours are not inferred from wreckage or from survivors' memory. They are on tape. The NTSB's 2017 report and the Coast Guard's Marine Board had the actual bridge in real time with the actual conversations. And what the tape shows is not a crew doing anything exotic. It shows professionals on a routine run, looking at a screen, discussing weather, and being wrong about a storm by a margin of a few hours, which is what this whole stretch has been building toward, and it is worth stating without softening. The problem was not lack of information. It was that the information moved on a slower clock than the hurricane. A forecast that is 6 hours stale is not a weaker version of a current forecast. It is a different forecast. Describing a storm in a place, the storm is not. Every system on that bridge was working. The ship was tracked, connected, and monitored. And a compressed timing mismatch between what the atmosphere was doing and what the screen was showing put a 241-meter ship inside a hurricane. Better instruments made El Faro's officers confident in a picture. They could not make the picture current. There is a class of storm that forms faster than the picture can be built at all, and it lives in the same cold water where ice has already been shown to kill quietly. Take Arctic air that has been sitting over sea ice at -20 or colder, and push it out over open ocean that is a few degrees above freezing. The temperature difference between the sea surface and the air a short distance above it can be 20 or 30 degrees. That is an enormous amount of heat and moisture moving upward, fast, in a small area. And what it builds is a compact spinning storm, 100 to 500 kilometers across, sometimes with a visible eye, with winds that reach hurricane force and snow heavy enough to erase the horizon. Meteorologists call them polar lows. Crews in the Norwegian Sea, the Barents, the Denmark Strait, the Labrador Sea, and the Gulf of Alaska have older names for them. The dangerous property is not the wind. It is the clock. A polar low can go from nothing to full strength in 12 to 24 hours and be gone inside 2 days. It is too small and too fast for the observing network that was built to track ordinary depressions. Before satellite imagery, these things effectively did not exist on any chart. They arrived on a vessel that had received a routine forecast a few hours earlier, and if that vessel was lost, there was nothing in the meteorological record to explain it. Today, most polar lows can be forecast 12 to 24 hours ahead. That is a real achievement, and set it against a hurricane, which is tracked for 5 days across an ocean, and you can see the size of the gap. 12 hours of warning at 10 knots is 120 miles of running room. In the Barents Sea in February, there is often nowhere within 120 miles worth running to. On the night of 8 of February 1974, in storm conditions in the Barents Sea north of Norway, the stern trawler Gol stopped existing. She was a big, modern vessel by the standards of the distant water fishing fleet, 66 meters around 1,200 tons, working the Arctic grounds out of Hull. 36 men were aboard, most of them from one city, many of them from the same few streets. No distress signal was received. Nothing. Her loss was not even suspected until $10 February, after she had twice failed to make a routine radio report. The search that followed covered the sea and produced one lifebuoy, recovered 3 months later. Into that vacuum came a story, and the story lasted 30 years. Hull trawlers had, at times, been used to gather intelligence on Soviet naval activity in those waters, and it became widely believed in the fishing community, and beyond that, the Gol had been engaged in that work, and had been taken, boarded, sunk, or otherwise removed by the Soviet Union. Families lived inside that version for a generation. It was not a fringe theory, it was raised in Parliament and pursued in the press. Look at what is actually happening there, because it is the same thing that happened to the Waratah. When a vessel disappears with no wreckage, no bodies, and no transmission, the absence does not stay empty. Something fills it. In 1909, it was a theory about a ship that rolled badly. In 1974, it was espionage. The absence is doing the work, not the evidence. In 1997, 23 years after she was lost, a search team of Norwegian salvage specialists, commissioned for a British television documentary, found the wreck of the Gol on the seabed, at a position where a Russian skipper had reported snagging his nets on something. A government-funded survey in 2002 examined the wreck in detail and recovered human remains, which were identified by DNA. A formal investigation was reopened, and it reported in 2004. The finding was almost insultingly ordinary. She had flooded. Her fish-loading hatches, the chutes through which catch and waste pass in and out of the factory deck, were open, along with weather-tight doors leading below. In a heavy following sea, water coming aboard the working deck had a path directly into the ship. Once inside a large open factory space, it did what water in a large open space always does. It ran to the low side and stayed there, and the vessel's ability to right herself went with it. She would have gone over and down in a very short time, in the dark, with no opportunity to send anything. 36 men, and the cause was open hatches on a working deck in a storm. Nobody involved was foolish. Those chutes are open during processing because that is how the work is done, and closing them at sea in bad weather means stopping fishing, which means a trip that does not pay. The habit of running with them open in weather that had always been survivable was, like everything else in this story, a margin being spent invisibly. And the reason it took 30 years to establish is that the ship was on the bottom of the Barents Sea, and nobody could look at her. This is the pattern that keeps repeating across every case here. The answer is almost always in the wreck. The wreck is almost always unreachable, and in the meantime, the loss is explained by whatever is available. Instruments and deep-water survey are what ended that, not argument. Draupner's laser, the satellites over the Atlantic, the surveys of the Derbyshire, El Faro's recorder at 4,500 meters, the Gol in 1997. There is a modern complication in the polar low story that deserves an honest treatment rather than a dramatic one. As sea ice retreats, more open water appears at high latitudes, which sounds like it should mean more of these storms. More warm sea for cold air to cross. It also means the cold air itself is less cold, and the reservoir of very cold air sitting on ice is smaller, which cuts the temperature contrast that drives the whole process. The published research does not point in one direction. Some work suggests polar low activity may decline in parts of the Nordic seas while shifting further north into waters that used to be frozen. That is genuinely unsettled, and anyone who tells you confidently that Arctic storms are simply increasing or simply decreasing is ahead of the evidence. What is not unsettled is where the ships are. Fishing fleets, cargo traffic, and offshore work have all been moving north as the ice season shortens, into waters where the observation network is thin, the harbors are far apart, and a storm can build to full strength between one forecast and the next, which sets up the last and largest case because there is one stretch of water where none of this is a local feature. Look at a globe from underneath. Between roughly 50 and 60 degrees south, there is no land. South America ends at Cape Horn, Africa ends far to the north, Australia and New Zealand end north of it, and Antarctica has not begun. The entire latitude band is water all the way around, with nothing in the way. That is why the Antarctic circumpolar current exists. It is the only current on Earth that goes all the way around without hitting anything, and it is by a wide margin the largest. The first serious estimates from the International Southern Ocean Studies program in the 1970s and 1980s put the flow through Drake Passage at about 134 spheredrupes. A spheredrup being 1 million cubic meters per second, so roughly 134 million cubic meters of water every second. A later program measured 141. Then between 2007 and 2011, an array of moored instruments strung across the passage with much better resolution produced a figure of 173.3 spheredrupes, about 30% larger than the number that had been used as the benchmark in climate and circulation models for decades. That measurement is barely 15 years old. We were wrong about the size of the biggest current in the world by a third. And we found out with instruments, the same way we found out about rogue waves. Now put weather on top of it. The same absence of land that lets the current run also lets the wind run. Depressions circle Antarctica continuously, and the westerlies they drive have unlimited fetch, no coastline anywhere to interrupt the process by which wind builds waves. Swell in the Southern Ocean grows to sizes that simply are not available in enclosed seas, and it keeps going until it runs into something. The first thing it runs into is Drake Passage, where South America and the Antarctic Peninsula pinch the gap down to about 800 kilometers and where submarine ridges cut across the flow and shoal it. Squeeze the current, put ridges under it, and drive Southern Ocean swell into the whole arrangement. Every mechanism named so far is present in that one passage at industrial scale. For 4 centuries, that was a place people went because they had to. Rounding Cape Horn westbound under sail meant beating into the prevailing wind and the prevailing current at the same time, for weeks, and ships did it because there was no canal and no alternative. Crews took the risk as the price of a cargo. Nobody has to go now, which makes what happens next more interesting, not less. Antarctic tourism has grown from a small specialist business into an industry. Recent seasons, by the operator's own association figures, have carried well over 100,000 visitors south, most of them across Drake Passage in expedition ships, most of them in a window of a few months. They go because the ships now exist, because the passage takes 2 days instead of 2 weeks, and because the place is extraordinary and people want to see it. All of that is understandable, and none of it is illegitimate. It also means that on any given day in the austral summer, there are thousands of people in one of the most exposed pieces of ocean on the planet, in a region with no coast guard, no rescue infrastructure, no airfield within useful range for most of the peninsula, and no hospital. The nearest help is another cruise ship, That is not a metaphor. The operators run a mutual assistance arrangement precisely because there is nothing else. On 23 November 2007, that arrangement got tested. The MS Explorer was a small, ice-strengthened expedition ship with a long history in the Antarctic trade. She had effectively invented the business. She was in the Bransfield Strait near King George Island with 154 people aboard when she struck ice and holed her hull. The damage was not large. The breach was described as roughly the size of a hand. Small hole, right place, and the ship was finished. Water came in faster than the pumps could handle. The master ordered abandon ship. In the small hours, in the Southern Ocean, everyone aboard got into lifeboats and life rafts and got clear. Then they waited. The Norwegian coastal ship Nord-Norge, working the same area, diverted and picked all 154 of them up, a process that took hours in cold water. In open boats, every person survived. The Explorer stayed afloat for about 20 hours and then sank. The Liberian investigation into the loss identified something specific and instructive about the master's judgment. His ice experience was largely Baltic. Baltic sea ice is frozen seawater, comparatively soft, and a strengthened hull can push through it. The ice around the Antarctic Peninsula includes hard glacial ice, land origin ice, which behaves like rock. Experience that had been correct and hard won in one place was wrong in another, and there was no obvious signal to tell him so. That incident is usually filed as a success, and in the most important sense it was. 154 people went into the Southern Ocean in small boats, and 154 came home. It should also be read the other way. The rescue worked because another suitable ship happened to be within a few hours steaming. Change that one fact, and the same event produces a mass casualty with no available response. The margin was not built into the system. It was a coincidence of scheduling. 15 years later, the passage demonstrated the other half of its repertoire. On the night of 29 November 2022, the expedition ship Viking Polaris was heading north from Antarctica toward Ushuaia, southeast of Cape Horn, in Drake Passage. At about 20 to 11 in the evening, a breaking wave struck the side of the ship. It shattered the windows of several cabins. One passenger was killed, and others were injured. The Norwegian Safety Investigation Authority examined it and found that the cabin windows could not withstand the load a breaking wave delivers. That is the Draupner problem arriving at the passenger deck. A breaking wave does not push, it hits. A slam load delivered in milliseconds by a mass of water moving at speed, which is a completely different kind of force from the steady pressure a hull is designed for. The ship was not sunk, was not disabled, and completed her passage. A single wave reached in through a window and killed someone in a cabin. And the modern element that ties this to everything before it is the one that gets discussed most and understood least. The Antarctic Peninsula is one of the fastest warming regions on the planet, and the sea ice around it has changed in timing and extent. It is tempting to read that as the region becoming more accessible and therefore safer. Be careful with that. Sea ice damps waves. A field of ice absorbs and scatters wave energy, and behind it the water is calmer. Take the ice away and swell, that would have been broken up, now runs unimpeded into coastlines, anchorages, and ships that were previously sheltered. Less ice does not mean less force. It means the force arrives in places that were not previously exposed to it. At the same time, the ice that remains is more mobile, moving faster, in less predictable patterns, which is precisely the condition in which a route that was open on the way in is closed on the way out. The season also gets longer, which means more voyages, earlier and later, into shoulder periods with worse weather and less daylight. Capability expands, and exposure expands with it. So the honest summary of what is changing down there is not that it is getting safer or more dangerous. It is that a familiar hazard is weakening while a different one strengthens. An operating experience built on the old balance is quietly going out of date, which is the same trap the explorer's master fell into with Baltic ice, at the scale of an entire industry. So gather it up, because by now, the shape of the thing should be visible, and it is not the shape most people expect. The stretches of water that professional mariners genuinely respect are not a random collection of rough places. They fall into a small number of families, and each family is defined by a specific physical trick. There are the places where a strong current runs against the prevailing swell, and the water compresses the waves into something short and steep and out of proportion to the wind. The Agulhas and the Wild Coast, the Mozambique Channel, the mouth of the Columbia, the shoals off Cape Hatteras where the Gulf Stream meets the cold water coming south, the entrance to Cook Strait, the tidal races of the Pentland Firth. There are the places where deep ocean swell climbs onto a shallow shelf, and the seabed does the same job the current does. Bass Strait, the Celtic Sea off southwest Ireland, the Grand Banks, the Eastern Bering Shelf, the Bay of Biscay, where the Atlantic runs up onto the European shelf, the banks around Sable Island, the North Sea. There are the places where land squeezes the wind, the gap winds that scream across the Gulf of Tehuantepec through a break in the mountains of Mexico, the willywaws that fall off the peaks into the Strait of Magellan, the channel between Maui and the island of Hawaii where the trades accelerate, Cook Strait again, which qualifies twice. There are the cold places, where the sea stays liquid under an atmosphere well below freezing and spray turns into structural weight, the Bering, the Sea of Okhotsk, the Gulf of Alaska, the Denmark Strait, the Labrador Sea. And there are the places whose only feature is that nothing interrupts them. The Southern Ocean, the Drake Passage, Cape Horn, the approaches to the Antarctic Peninsula, the surf coast of Namibia where the Benguela fog closes over a shore with no harbors, 20-odd stretches of water, 5 mechanisms, and the reason experienced crews treat them differently from ordinary rough weather is that all 5 produce force out of proportion to the wind that is blowing at the time. That is the actual answer to the question this started with. It is not that the storms are worse. In several of these places, the storms are unremarkable. It is that the geography converts an ordinary storm into an extraordinary sea, and does it in a specific, repeatable, mappable way, which is why the shallow ones kill more than the deep ones. Deep open ocean, far from everything, produces waves that are large and long, and a ship rides them. A shelf, a bar, a strait, a bank, or a current edge produces waves that are shorter than the vessel and steeper than anything it was designed for, and it produces them in exactly the places people have to go. Because shelves are where the fish are, straits are where the roots are, bars are where the ports are, and current edges are where the free speed is. The danger is concentrated in the useful water. That is not bad luck. It is the same physics that makes the water useful. Now put the human layer back on top, because the physics alone has never killed anybody who stayed home. The people who lived beside these places before engines had a working answer, and their answer was to read the water and decline. That method is still the only complete defense, and it is the one thing modern operations structurally cannot do. Because the whole point of a schedule is that it does not consult the sea. A race starts on 26 December. A crab season opens in January. A charter is fixed. A cruise itinerary is sold 18 months in advance. Puerto Rico needs its freight on Thursday. Every technology since has improved a piece of the problem and left that part untouched. The engine removed the lee shore and made departure a commercial decision instead of a meteorological one. Steel and welding produced hulls that were longer and stronger and, in current-shortened seas, discovered a new way to fail across the middle. Radio meant a ship could report her position and her distress from anywhere, which is why we now know precisely where people were when nobody could reach them. Forecasting became genuinely excellent, and then arrived on a bridge 6 hours stale while a hurricane turned. Semi-submersible platforms defeated the wave and were defeated by a window. Immersion suits, life rafts, EPIRBs, and rescue swimmers cut the death rate hard and did nothing about how long a helicopter takes to fly 300 miles. So the loops close like this. The Waratah was never found because the mechanism that most likely took her is fast, and the current that made her passage quick is very good at dispersing what is left. That is not a solution. It is the reason there will not be one. The strongest structure failed first because strength was applied to the sea, and the sea went around it, through a port light, into a control panel, and out through a chain locker that nobody had made watertight. And the best-informed bridge in this whole account sailed into the worst quadrant of a hurricane, not because anyone was careless, but because the picture on the screen was a few hours behind the sky. And a few hours is the entire margin. None of these places has become safer in the way people assume. They have become better documented, better warned, better equipped, and much better attended after the fact. The frequency of the traps has not changed at all, because the seafloor has not moved. The currents still run where they run. The fronts still come through on schedule, and the cold air still sits over warm water every winter. What has changed is that more people are out there, in more months of the year, further from help, with more confidence. The Antarctic season stretches longer each decade. The Bering Fleet works the same weeks in worse ice conditions than the forecasts describe. Traffic through the Agulhas has not declined. The Columbia Bar handles the same commerce it always did, and the ships are larger, which is where this ends, in a place small enough to see. Go to Cape Disappointment on an ordinary winter afternoon at the mouth of the Columbia, and there is a 47-foot motor lifeboat in the water with her engines running, orange and white, low, heavy, built to be rolled and come back. There are 4 people aboard, strapped into their seats, wearing dry suits and helmets, doing nothing in particular. They are watching the ebb. Out past the jetty, the bar is starting to stand up, the way it does when the river runs out against the swell, and the line of white that marks it is getting longer and closer together as the afternoon goes on. Somewhere out there, a boat is deciding whether to come in now or wait for the flood, and the decision is being made by a person looking at the same water from a lower angle with a fish hold to fill and a market on Monday. The crew in the lifeboat will sit there until the light goes. If nothing happens, the shift ends. They will tie up. Someone else will take the boat, and it will start again tomorrow. 2,000 vessels have gone down in that 3-mile stretch. The counting started in 1792, and nobody has had cause to stop. The boat is idling. The tide is turning. The bar is building the way it builds on every ebb, and somewhere out past the swell line, a skipper is doing the arithmetic on whether there is still time to come in. The crew in the orange boat are sitting there because sooner or later that arithmetic comes out wrong, and when it does, 3 miles is the entire margin.